Recording in progress.
Okay, now we just saw that if we start with a system, we can solve the system. If the system is degenerate, if, in this case, subsequent rows are linear combinations of previous rows, you're always going to end up with a 0 equals 0. In this case, it's a 2 by 2 system in 2 dimensions. We end up with just one equation, which can be reduced to this, which can come down to show that the solutions form the set of vectors here and here. This vector is called your particular solution, and this is the solution to the null space. Okay, it's the characteristic solution, and there are other words that are often used, and sometimes students make up their own words to describe these, and I'm not going to repeat those. Okay, and then we get this picture. Okay, we get the span of this vector, which is set of all t's times this vector. There's your null space in orange, and we get this line, okay, the row space, and those are perpendicular. The dimension of the null space is 1, the dimension of the row space is 1, and these two vectors span all of R2. Now we worked through all the details of this, and I don't know if I just said it, but the row space is orthogonal to the null space, meaning in Euclidean spaces it's perpendicular. In other more general spaces we use the word orthogonal rather than perpendicular, but when we visualize it, it kind of means the same thing. So we have this picture of null space and row space. Also, all our solutions to the system, that's the red line, consist of points on the null space or vectors in the null space displaced by whatever particular solution you want, whatever specific solution to the equation you happen to get, depending on how you've reduced the system. So that any of these purple vectors correspond to solutions to both of these equations. We've concluded that then, at least in this case, that the null space is perpendicular to the row space, orthogonal to the row space, and that the rank plus the nullity is equal to the dimension of our space. We went through some details here, and then I claimed, hadn't proved, I claimed that this is always so for any n by n matrix. I haven't even proven that it's always so for 2 by 2 matrices. But the example kind of shows how this is geometrically interpreted. Now what I want to do is I want to go ahead and just show you without going through the details, because the details simply come down to some more matrix reduction and so forth. Okay. If the matrix A reduces to and I didn't mention this is going to be a matrix in 3 dimensions. Okay. If this matrix reduces to, let's say, 1, 0, some number here, 0, 1, another number, and 0, 0, 0, 0, and actually I've written an augmented matrix, and I just meant to reduce the matrix A. So, okay, if the matrix A reduces to this, then the rank is 2, because the rank is the dimension of the row space. These rows are linearly independent. and they span the row space. So we have two linear independent rows. Now, if the matrix reduces to this, then the rows of the original matrix include two linearly independent rows, but not three. And that's because row operations don't change the span of a set of vectors. Okay, the set of rows, the span of that set is not changed by row operations. And not going to go into the details of that. We've established that. Okay, rank is 2. We get two linearly independent rows. Nullity is 1. One row of zeros. The matrix in this case is n by n for n equals 3. And now the rank plus the nullity equals n, because 2 plus 1 equals 3. Very simple to see what the rank and the nullity are. The row space is now the span of these two vectors. It's the span of the set 1, 0, asterisk, where again the asterisk can be any number depending on what the original matrix was. And this asterisk can be any number. Now let's be clear, this can be any number, this can be any number, and this number don't have to be the same even though they're represented by that asterisk. Okay, so there's your row space. Okay, it has dimension 2. And your null space is the set of solutions. And I'm not going to write it down because that really depends on the matrix. That's where you would write the solution to the matrix equation AX equals 0. AX equals 0 vector. Now I'm just looking at space here. These vectors are in 3 dimensions. So if we have x1, x2, x3, our row space would be spanned by 2 vectors. Okay, well the span of 2 vectors, 2 arbitrary vectors in the row space, and let's go ahead and use some colors here. Well, what I used for the row space in previous examples was just white chalk, so I'm going to do it that way. Okay, so we maybe have a vector here, and where is this vector? Okay, Well, to see where this vector is, we kind of have to maybe project down into the XY plane, and now we see that it comes out into the first quadrant, goes up, so we can kind of see where that vector is. And then we have another vector that I'll indicate maybe like so. And let's say this vector also comes out to the, well, it isn't in the first quadrant, but let's say that when we project this vector we get this. So we can kind of see where this vector goes. This vector kind of goes there. This vector kind of comes back here. If we put a sheet of glass over these two vectors, there's exactly one way that sheet of glass can be oriented to cover these two vectors, to lie on these two vectors, and that sheet of glass is a plane. Okay, so these two vectors are a basis. So I'd have done better to actually use this form of each vector. So yeah, it could look like this, but I'm going to destroy my picture here and draw something that's hopefully a better picture. Make it a little more obvious to you. Okay, the row space is the span of these two vectors, and each vector has a zero component in one of the coordinate directions. And I apologize, I maybe could have planned that out, but I didn't think of it until just now. Okay. This vector, 1, 0, asterisk, has a zero component in the x2 direction. So it's going to be a little easier to visualize this than what we just did, although that one I don't think is too difficult. This one comes out 1 unit in the x direction, and then whatever number of units in the x3 direction. It comes out 1 unit in the x1 direction, 0 units in the x2, some number of units in the x3 direction. So I can draw this vector any place. I'm going to draw points here, 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 and here on the axes to indicate unit distances. So this is the point 1, 0, 0, negative 1, 0, 0, 0, 1, 0, 0, negative 1, 0, 0, 0, negative 1, 0, 0, 1. Okay, the unit points on the axes. Okay, so 1, 0, asterisk, we have an x1 coordinate of 1, x2 coordinate of 0, and an x3 coordinate of whatever, so that this vector could be depicted like so, and we see from the dotted line, and maybe a little bit of shading, I don't necessarily want to do that, but I guess I will, that this triangle lies in the x1, x3 plane, and this vector is the hypotenuse of that triangle. Now actually, we don't know what star is. It could be anywhere above here or below here, but it's somewhere in the x1, x3 plane. 0, 1, asterisk means that the x1 coordinate is 0, the x2 coordinate is 1, and the x3 coordinate could be any number. So for convenience, I'm going to say, okay, well, let's say that the x3 coordinate is such that the vector goes up to this point. And this vector, of course, lies in the x2, x3 plane. So this vector is coming out this way and going up. This vector is going over this way and going up. And now there's a plane that fits these two vectors, and it's fairly easy to see where that plane lies if you just try to visualize it. I don't want to try to sketch it because it gets too messy. Then you have the null space. Okay, now the null space is going to be spanned by some vector that you get when you solve the equation ax equals 0. And that vector has to be orthogonal or perpendicular to both of these. Okay, so let's just say that your null space looks like this. Now, we don't know where any vector is, but consistent with the way I pictured it previously, I'm going to draw a little blue vector here along the direction of the null space. This vector would be a vector we get when we solve ax equals 0. This is a line through the origin parallel to this vector. And this null space vector is orthogonal or perpendicular to these two vectors, so that the angle between this vector and, better use something besides white, the angle between this vector and the null space line in this case is a right angle, and the angle here is a right angle. And that's the picture you would have in 3 dimensions. Now there's another case. Maybe A reduces to a space with 2 rows of zeros. If that's the case, then your row space has dimension 1 and your null space has dimension 2. Meaning that now, if we want to use the color coding with orange for the null space, these two vectors would turn orange and the plane would be orange. And these two vectors would be blue because they indicate vectors in the null space. And this vector here would be white because it's the row space vector, and we'd have a white line. Now I'm going to actually draw that using all my drawing skills and looking for an available board, which I don't have, so I'm going to do it like this. If A reduces to it actually could be 1 asterisk asterisk. Okay, any vector at all, because, and that's going to happen because the second and third rows are multiples of the first row. So when you do your first step of reduction on the second row, it's going to give you all zeros. Do your first step of reduction on this row, it's going to give you all zeros. So A would reduce to this. Then row space is a span of in the null space is a span of 2 linearly independent vectors. Now you can reduce a matrix of this nature and solve for the null space and see how that works. Don't want to go into that detail. So our picture, first of all, the rank is 1. The nullity is 2, and to repeat it, because you can't repeat it too many times. Well, you can, but not yet. Okay, the rank is 1 because you have 1 non-zero row in your reduced matrix. Your nullity is 2 because you have 2 zero rows. And n equals 3, and the rank plus the nullity still equals n. So your n is 3, so you're going to be in 3 dimensions. Then your your row has basis vector 1 asterisk asterisk, and that's going to be just some vector, 1 unit this way, and then any number of units over and any number of units up. So well, that was ignorant. Let me try it again. And let me clear this so it doesn't smudge. Okay. So we have 1 unit here. We come over to some point here, and then we go up some distance here. And what I did was I drew the vector with its root here, its initial point, and the initial point always has to be the origin. Okay, so this is your vector 1 asterisk asterisk. Your basis for the row space, just set consisting of this vector, and your row space is here. Your null space is going to be spanned by 2 vectors. Okay, so your null space might be spanned by a vector here and a vector here. So these 2 vectors are the basis of the null space. And abbreviate that. Okay. This vector and this vector form the basis of your null space. Then your null space then consists of a plane through these 2, lying on these 2 vectors. It's the plane spanned by the basis of your null space. And that plane might look something like this. Now I'm going to attempt this. I don't know if the picture is going to end up making a lot of sense because I didn't take the time to plan it out real well. but it's going to be a plane. These two vectors lie on the plane, and the plane is perpendicular to your row space, so that angle between here and here is a right angle. Angle here is a right angle. And the angle between this vector and any vector from the origin out to a point here is going to be a right angle. Now that's going to be a little hard to visualize. I don't expect that anybody's had multivariable calculus, and I certainly don't expect, although it's possible, that people did much with geometry at all in prerequisite courses, because we've dumbed geometry out of the curriculum, making it a little more difficult to understand what you're seeing here. But you have multivariable calculus in your future. You need to understand this, and you need to understand some three-dimensional visualization. And hopefully you've done some of it. Most people have done at least a little bit. So anyhow, there's a picture. Now, these two pictures are, in a sense, dual pictures. Okay? It's like the function of your row space is now the function of your null space. So the row space here is spanned by two vectors and forms a plane, but now it's the null space that's spanned by two vectors and forms a plane. And your row space here was spanned by two vectors, forms a plane. Your null space here was spanned by one vector, forming a plane, and your null space here is now a plane. Okay, so row space in this case is a plane. In this case, it's a line. The null space in this case is a line. The null space in this case is a plane. And the only difference is, if you want to look at it this way, that here you have one row of zeros, so that you have two rows that are linearly independent and don't form zero. But you have one row of zeros here, you have two rows of zeros here. So you want to think through that. Okay, now we're going to actually do an example. Actually we're not, because I'm out of time for today, but we're going to go on and do an example that pretty much illustrates all of this a little more specifically.